This is a video on simplifying rational expressions. Something I need you to keep in mind is that rational expressions have fractions in them. So I'm just going to work through a couple of examples with you. These are similar to ones that you've received from us as part of your practice. One of the things that's kind of a fundamental idea that is worth writing down is that we can only cancel factors, not terms. Okay? So the idea here is that I have to factor these rational expressions before I can cancel anything out. I know you get a strong urge to try to cancel out the x's here, or maybe even 12 and 4 reduces to 3, something like that. But I can't do that because not every term is divisible by this denominator. That's the idea. I can't divide if not every single term in the numerator can be divided by the denominator. So what we do is to try to factor every piece of this rational expression so that hopefully we can then cancel out some of these common factors and eliminate them from the expression. All right, so the first thing we should always check with is greatest common factor. So on the top, I'm going to look for the greatest common factor, and that's going to be 3. So then I ask myself, okay, what do I multiply 3 by to get 3x plus 12? Because factoring is writing as a multiplication problem or doing reverse distribution. And so what do I multiply 3 by to get 3x plus 12? X plus 4. Okay, now the bottom doesn't have a common factor other than 1, so unfortunately I'm left with just that scenario. But the good thing is that I've now factored the numerator and the denominator, and I have a common factor of x plus 4. And since they're the exact same factor, one on the top, one on the bottom, they can cancel out. And then I'm just left with the 3 over 1. Now I just do a real quick check to make sure I don't have any remaining factors or things that can be simplified. I don't, so this would be my final expression. Now I'm going to make it a little bit more complicated, something that's got a more complicated factoring process than just greatest common factor. Now my denominator here is still going to be a greatest common factor scenario. Greatest common factor was 3. And I multiply that by x minus 7 to get 3x minus 21. That was no problem. Now I'll check for a greatest common factor in my top, but I'll realize that I don't have one other than 1 here. And so I'm left with other ways to factor. Now this is a quadratic, but this is also one of those special cases. So this is the difference of two squares. So it's that a squared minus b squared special case scenario that factors every time as a plus b, a minus b. Now, your challenge here, not only knowing that pattern, but also knowing what's a and what's b. So x squared is in my a squared spot, so that would mean that a would be x. So that would be the number that I'm going to put everywhere I see my a's. Okay, my b value, which will be the square root of b squared, or the square root of 49, is 7. Now don't worry about the negative because that's going to get taken care of in my factoring pattern. But I'm going to replace my a and my b with x and 7 respectively. So this thing on top factors as x plus 7, x minus 7. Now the advantage to this is that goes quickly if you know the factoring pattern. If you can't remember the factoring pattern, you could just put a 0 here for your b term, and you can use that to help you factor in a traditional way, which we'll do one like that a little bit later on. But if you remember that factoring pattern, that special case of the difference of two squares, then it goes a little bit quicker. Well, so now I look at this in factored form, and I see that I have an x minus 7 factor on the top and the bottom, so those can cancel. I'll be left with x plus 7 on the top and 3 on the bottom. And because neither x nor 7 can be divided by 3, let alone both of them be divided by 3, I have to stop here. All right. All right, taking it up one more level on you. Now I've got to try to factor a trinomial quadratic on the top and a special case difference of two squares on the bottom. So the difference of two squares is going to probably be a little bit easier for you. This is another one of our scenarios, the a squared minus b squared. Oops. A squared minus b squared that factors as a plus b, a minus b. And in this case, my a value is actually going to be a. And my b value is going to be the square root of 25, which is 5. So that bottom factors. Again, that goes quickly if you remember that factoring pattern. Now the top, unfortunately, not as quick. We have to factor that trinomial. So I'm going to come down to here, and I'm going to do some factoring with that trinomial. Now this is going to be, I'm going to do the grouping method. There's lots of different ways to try to factor. I'm going to do this by grouping. So I'm going to turn it from a 3-term polynomial into a 4-term polynomial. Some folks do this with a box. You are welcome to do that. I'm just going to show you what I feel is the most efficient way of factoring, provided this quadratic polynomial can be factored. So we start by multiplying the a value, which is here, and the b value, which is here. We multiply those guys together. So the a value 1, the b value of 20, 1 times 20 is 20. So now I'm looking for the factors of 20 that add up to this middle term 9. So we're going to break that middle term apart so that I turn it from a 3-term polynomial to a 4-term polynomial. So I'm looking for all the different ways that I can multiply two numbers and get 20. Well, that's 1 and 20, 2 and 10, 4 times 5. Which one of those three pairs adds up to 9? 4 times 5. So I'm going to break that middle term into 4a plus 5a so that I now have a 4-term polynomial that I could then make two groups. So here we go. A squared and 20, they weren't changed at all. They're still the first and the last terms. But then instead of having a 9a, I'm going to have my 4a plus my 5a in the middle. Now, these expressions are equivalent. They're the same thing, but I've now turned it from a 3-term into a 4-term by uncombining like terms in the middle. So now that allows me the ability to factor by doing the GCF on each of these binomials. So what's the greatest common factor between a squared and 4a? That would be a. So then that leaves me with a plus 4 here. Keep my plus sign to keep everything separated. What's the greatest common factor between 5a and 20? That would be 5. So then I'm left with a plus 4. Now I know that I've done this right when my two factors match here. If they don't match, then you've done something wrong and you need to stop and go back. But the common factor here is a plus 4, so I'll pull that out front. And what's remaining here and here make my second binomial pair in my factors, a plus 5. So now this is the factored form of what my numerator was. So I could take that and move it here. So that's a plus 4 times a plus 5. And now I've got the factored form of my numerator and the factored form of my denominator. And I can simplify by canceling out these a plus 5s. And I'm left with a plus 4 over a minus 5 as my simplified expression. Now the last example that I'm going to give you is not more complicated than our previous one. It just looks different. Remember, we always check for greatest common factor. So even though I've got a cubic on the top, I still check for greatest common factor. They both have a factor of 2. 2 and 8 both have a factor of 2. But then you take a look and they both have an n to some power. The way I think about it is they both have at least how many or n to the what power. So they both have at least n squared. So the greatest common factor was 2n squared. Now, what do I multiply 2n squared by? To get 2n cubed plus 8n squared, that would be n to get 2n cubed, and that would be 4 to get 8n squared. Now we've taken care of the top. Let's do GCF on the bottom to see if there's any more factoring that can be done here. The 5 and the 20 have a common factor of 5. We have an n squared and an n to the first, so they both have at least n to the first. So now what do I multiply 5n by to get 5n squared plus 20n? That would be n plus 4, and we have a common factor now, which means we could cancel out there. So these two cancel out, and I'm left with 2n squared over 5n. Now, there's no more plus or minus signs, so I don't have any terms that I need to worry about. So I can still continue trying to simplify by canceling things out. Now, my 2 and my 5, I look at separately from my n's. My 2 and my 5, I try to reduce those like I've been reducing fractions for a long time. Unfortunately, 2 and 5 won't reduce, so that's going to still be part of my final expression. But n squared and n, they will simplify. When we divide like bases, we subtract their exponents. So this would be like n to the second minus n to the first is essentially what's going on there. Now, I'm sorry, I misspoke. Let me try this again. This is like n to the 2 minus 1. That's how that would work. So you're only subtracting their exponents. You're not actually subtracting the n's themselves. So 2 minus 1 would leave me with 1n and then my 5 on the bottom. And this is my simplified expression. Again, how do I simplify like bases? I subtract their exponents when I'm dividing.